So, in the previous lecture we were discussing the rate of deformation tensor. This is the gradient of the velocity, which we had written, you recall, as Ex, Ey, Ez. This is the rate of deformation tensor, and last time we had separated it out into 3 components. 1/3 the divergence of the velocity times the isotropic tensor, which basically represents radial expansion or compression around a point, which results in a change in volume of the due to this kind of expansion or compression, the fluid volume has to change at that point. And this will turn out to be 0 if there is no volumetric expansion or compression, or if the fluid is incompressible, so that the density does not change. In that case, since the density in a material element does not change, the mass is conserved and therefore the volume has to remain the same. Therefore, the shape of that differential volume can change, but the volume itself cannot change. The second part was the symmetric traceless part, which represented extensional strain. The symmetric traceless part, which represented extensional strain, and if you recall, the displacement due to this kind of strain was extensional along 2 axes and compressional along the orthogonal axis. So, it is extensional along one axis and compressional along the orthogonal axis in 2 dimensions. So, that the volume which is initially like this expands along one direction and compresses along 2 directions. That is in 2 dimensions, and I had justified that for you in the previous lectures. And then there was the rotational part, the antisymmetric part, which basically represents solid body rotation. In which case the velocity vector is perpendicular to the displacement from the origin, and this basically represents a solid body rotation. So, that was the simple 2-dimensional picture, and in 3 dimensions I told you that this extensional part, symmetric traceless part, can be written, because it is symmetric and traceless, the tensor is symmetric and traceless, therefore, the eigenvalues are real and the eigenvectors are orthogonal, and this can always be written as in a coordinate system in which the coordinate directions are along the eigenvectors. This can be written as lambda 1 0 0. And this represents in a coordinate system that is aligned along the along the eigenvectors of this matrix locally. Note that all of these are functions of position, they vary as you go to different locations. So, in a coordinate system that is aligned locally with the eigenvectors, there is expansion along directions where the eigenvectors are positive, okay, and there is compression along the directions where the eigenvectors are negative. Note that the sum of the eigenvectors has to be 0 because the trace of the matrix is 0. Therefore, you can have two directions of expansion and one compression, or one direction of expansion and two compression, and so on, okay, or a planar strain where there is expansion along one direction, compression along the other direction, and there is no deformation along the third direction if the eigenvalue in that direction is 0. So, that is for the symmetric traceless part of the rate of deformation tensor, and this is what is called extensional strain. Okay. And this is in general non-zero even for an incompressible fluid. Okay. Then there was the antisymmetric part, okay, of the rate of deformation tensor. Okay. And I told you that the components of the antisymmetric part can be expressed in terms of the components of the vorticity omega, which is del cross V. Okay. So, this is a vector that can be written as omega x E x plus omega y E y plus omega z E z, where omega x is equal to partial V z by partial y minus partial V y by partial z. Okay. A partial okay. And omega z is equal to those were the components of this vorticity vector, and the symmetric traceless part could be written in terms of these components as 0 half omega z minus half omega y, okay, minus half omega z, 0 half omega x, okay, half omega y minus half omega x, and 0. Okay. So, antisymmetric tensor in 3 dimensions, the 3 by 3 tensor, antisymmetric, the trace, the diagonal elements have to be 0, and the 3 off diagonal elements are related to each other. So, there are only 3 independent elements, and these are the components of this vorticity vector. Okay. And I showed you that the velocity, the difference in velocity between two nearby locations can be written in terms of this vorticity vector. Okay. Half of or you can write it in vector notation as delta v, okay, delta v vector is equal to half of omega vector cross delta x vector. Okay. This gives you the same relation. Okay. And this represents solid body rotation with angular velocity equal to half the vorticity. Okay. So, this represents solid body rotation with angular velocity equal to half the vorticity. Okay. So, and the direction, the axis of rotation is along the vorticity vector, okay, because the angular velocity vector, which in this case is half the vorticity vector, is directed perpendicular to the plane of rotation. Okay. The angular velocity vector is directed perpendicular to the plane of rotation. So, at each point in space you can make this separation into three different components: the radial expansion or compression, the symmetric traceless part, the extensional strain, and the solid body rotation locally at that point. So, let us solve this for a case that we have already seen before. Okay. The pressure driven flow in a channel, okay, of height h, okay, Bx, sorry, x and z are the orthogonal coordinates, and the velocity profile is a parabolic profile which looks something like this for the pressure driven flow in a channel, and the velocity is unidirectional. It is only in the x direction, it is only a function of z, and Vx is equal to 6 V average into z h minus z square by h square, okay, where V average is the average velocity. Okay. And for this we have to separate out the velocity into its different components: isotropic, symmetric, traceless, and antisymmetric. And obviously the velocity is a function of z. So, these components also will be a function of z. Okay. So, let us go through that exercise and try to find out what are the isotropic, symmetric, traceless, and antisymmetric part of this velocity. You can see that there is only one element in the rate of deformation tensor in this case that is non-zero, that is partial Vx by partial z. Okay. And if I take the derivative with respect to z, I get this as 6 V average into h minus 2z by h square. Okay. This is 6 times V average times h minus 2z divided by h square. Okay. Okay, so what is the rate of deformation tensor? Okay, grad V is equal to, if you recall, it has only one non-zero element. So, this is equal to this has only one non-zero element. Okay. And now this can be decomposed into symmetric, traceless, antisymmetric, and isotropic. Isotropic part is 0 because the diagonal elements are 0. This is an incompressible flow. Okay. And for an incompressible flow, the divergence of velocity is 0, and therefore the trace of the rate of deformation tensor is also 0, okay, for this particular case. Therefore, the symmetric traceless part is going to be equal to, okay, okay. So, this is the symmetric traceless part. I take this matrix, okay, add to it its transpose, and when you add the transpose, this term on the bottom left goes to the top right. Okay. You interchange the rows and columns, the term on the bottom left goes to the top right. So, add that and then divide by 2, and that is why you get a factor of 3 here. Okay. So, this is the extensional strain. Okay. What kind of strain is it? Okay. So, in order to determine what kind of strain it is, we have to determine the eigenvalues and the eigenvectors. Okay. So, the eigenvalues are determined from the auxiliary equation, okay, minus I lambda, okay, where lambda is the eigenvalue. Okay. The determinant of that has to be equal to 0 in order to determine the eigenvalues. Okay. So, this implies that minus lambda 0 okay. The determinant of this has to be 0. Okay. You can calculate the determinant quite easily. It just gives you minus lambda cubed, okay. That is the first, okay, the first element there. Second element is multiplied by 0. The third element is plus 3 by z square into, okay, the element here, okay, multiplied by this matrix, okay, multiplied by this matrix. Okay. The determinant of that matrix is going to be equal to lambda into 3 VAV into h minus 2z by h square. My apologies, this should be an h square here. Okay. This has got to be equal to 0. Okay. And as you can see, this entire equation is multiplied by lambda. So, I can take that out as a common factor. Okay. So, this becomes lambda square and this lambda has been taken out. So, this whole thing is equal to 0 and I get 3 solutions. Okay. Lambda is equal to 0, okay. Lambda is equal to plus 3 VAV So, this is lambda 1, 2 and 3. Okay. These are the 3 eigenvalues. One of the eigenvalues is 0, therefore, this is planar extension. There is extension along one direction, compression along the other direction, and there is no deformation along the third direction. Okay. And we can now find out what these directions are, okay, by the relation, okay, E minus I lambda dotted with the unit vector. This has to be equal to 0, okay, where E is the eigenvector, okay, for corresponding to that particular eigenvalue. Okay. So, for the 0 eigenvalue I have, okay, okay, into Ex has got to be equal to 0. Okay. that is how you determine the eigenvector for corresponding to the eigenvalue, first eigenvalue, that was 0. Okay. And you can easily, the solution for this is going to be equal to E1 is equal to Ey. Okay. Okay. Because if Ey, the component Ey is equal to 1, okay. So, if the component Ey in this eigenvector is equal to 1, Ex and Ez are equal to 0, this relation is identically satisfied. Okay. That means that the direction in which there is no extension or compression is the y direction. Not surprising, this is a two-dimensional flow, okay, in which the y direction is perpendicular to the plane. Okay. Since this is a two-dimensional flow in which the y direction is perpendicular to the plane, you would expect that there is no expansion or compression in the y direction. Okay. E2. Okay. Now, here I have to substitute this, okay, for the eigenvalue. So, this equation now gets modified. Okay. The diagonal terms in this equation are minus 3 VAV into Z minus 2 H minus 2 Z. Yeah. H square. Okay. And so is this diagonal term minus 3 VAV into H minus . Okay. So, these diagonal terms are minus lambda. Okay. These diagonal terms are minus lambda. Okay. So, therefore, this relation is satisfied if the component along the x direction and the component along the z direction of the unit vector are equal. Okay. If the component of the along the x direction and the component along the z direction are equal. If these two are equal, then this equation, this matrix equation is identically satisfied. Okay. Therefore, the second eigenvector is going to be equal to Ex plus Ez by root 2, because this has to be normalized. Okay. This has to be normalized. Okay. The eigenvector corresponding to lambda 3, okay, which is perpendicular to both of these. Okay. In that case, there would be a plus sign here, because lambda 3 is equal to minus lambda 2, and you can easily verify that the third eigenvector is going to be equal to Ex minus Ez by 2. Okay. So, what this implies is that at any particular location, okay, if I have a shear flow with a velocity in this direction, okay, the direction of extension is along the 45 degree to the x axis. Okay. So, if this is the x axis and this is the y axis, the direction of extension is along the plus 45 degree for this, okay, and the direction of compression is along the minus 45 degree. Okay. So, I have compression along this direction and extension along this direction. Okay. So, let me draw it a little more larger. Okay. If I have a velocity gradient that looks like this, okay, then I can separate it out into a direction of extension and a direction of compression. Okay. Okay. So, the compression along this axis and extension along this axis, okay, gives a flow field that looks something like this. Okay. That is, if the shear is positive, dVx by dz is positive. Okay. If dVx by dz is positive, then you have expansion along the plus 45 degrees and compression along the minus 45 degrees. Okay. It is positive for the lower half here. Okay. For the upper half it is negative. Okay. For the upper half it is negative. Okay. The slope is negative. Okay. Therefore, the direction of compression and expansion will change. Okay. So, that is how you identify the directions of compression and expansion locally at each point within the flow. Okay. So, you take the symmetric traceless part of the rate of deformation tensor, find out its eigenvalues and find out its eigenvectors. Eigenvalues tell you whether there is compression or expansion, eigenvectors tell you the directions in which there is compression, the direction in which there is expansion and the direction in which there is no shear. Okay. So, this was the symmetric traceless part. The final component will be the antisymmetric part. Okay. Okay. And for this matrix that we have here, okay, for this matrix that we have here, okay, it is easy to determine what is that antisymmetric part. Okay. So, this is going to be equal to 0 0 minus 3 VAV into h minus 2z by h square So, this is going to be the antisymmetric part. Note that we had identified this in terms of the components of the vorticity vector. Okay. This was equal to half omega z, this was equal to minus half omega y, okay. This was equal to half omega x, this was equal to minus half omega z, this was equal to half omega y, this was minus half omega x. We had done this identification of the elements in terms of the vorticity vector. Okay. What that implies is that for this deformation omega y is equal to 3 V average into h minus 2z by h square. Omega x is equal to 0, omega y is equal to 0. Therefore, the axis of rotation is in the y direction perpendicular to the plane of the flow. Okay. That is also expected. Okay. So, in this kind of a shear flow, you will combine this with a rotation about the center that goes like this. Okay. So, these two types of deformation put together give you a linear shear flow. The rotation in this case will be in the along the plus y direction. If the velocity gradient is positive, it will be in the plus y direction according to the right hand rule. Okay. Okay. X, z and y is into the plane, okay, in the right hand rule. So, that if I take x cross y, I get the z direction according to the right hand rule. Okay. So, this rotation is in the y direction. Okay. If the velocity gradient is positive, it will be in the minus y direction if the velocity gradient is negative. Okay. So, in this case, for example, when you are in the bottom half of the channel where 2z is less than h. Okay. Okay. So, this is the z direction, this is the x direction, this is z is equal to h by 2, z is equal to h, z is equal to 0. Okay. If you are in the bottom half of the channel, okay, if you are in the bottom half of the channel, okay, the slope is positive. Okay, the slope is positive, extension along the plus 45 degrees from the x axis, compression along the minus 45 degrees from the x axis, rotation is along the plus y direction into the plane. Okay, in the plus y direction into the plane as shown in this figure. On the top half, the z is h is less than z is greater than h by 2. Therefore, the direction of omega y reverses and the direction of extension and compression also reverses. So, any flow can be expanded in these terms, in terms of these symmetric traceless part, antisymmetric part, isotropic part. For incompressible flow, isotropic part is 0. The eigen values of the symmetric traceless part tell you the rates of compression and expansion. The eigen vectors tell you the direction of compression and expansion. Eigen vectors are orthogonal. For the antisymmetric part, the vorticity tells you the axis of rotation, and 1/2 of the vorticity is the angular velocity for the rotation, for the solid body rotation around that axis. So, this is the summary of the rate of deformation tensor. We had first discussed the stress tensor, we had then discussed the rate of deformation tensor. In the next lecture, we will examine the relation between those two, the stress and the rate of deformation tensor, which is the constitutive relation, Newton's law for viscosity in tensor form. We will continue that in the next lecture. I will see you then.